there are other things. For pressure measurement, we have the barometer, right? And we have the manometer. These are two different devices, barometer and manometer. Barometer is used to measure barometric pressure, which we call the air pressure out here, or atmospheric pressure. Manometers are used to measure gases in containers like this. What's the pressure of the gas inside a container? Like a tank, an air tank, or whatever. We use manometers. There are other devices too, not just manometers, but there are a whole bunch of different pressure gauges that are available out there. We're just looking at two, the most basic ones. When we measure pressure, we have to keep in mind, are we measuring gauge pressure, which is pressure relative to the atmospheric pressure, or are we measuring absolute pressure? The details, you don't have to memorize the definitions here. Just barometer, manometer, gauge pressure, absolute pressure. Those are just keywords there. This is the way the manometer works. The manometer works, it's like a seesaw or a triple beam balance. And so if you see there's yellow gas in the container here. Inside here we have the weight of the gas. Outside here we have the weight of the atmosphere. Which one weighs more, the gas or the atmosphere? This is a seesaw. So the atmosphere is on the right side, the gas is on the left side. Which side weighs more? The gas. The gas weighs more. And so that's it. Over here, the gas is on the inside, the atmosphere is on the outside. Which one weighs more? The atmosphere. The atmosphere weighs more. And so this is the basic operation of a manometer. Manometer, you're going to have this seesaw. This is mercury here. Put in here. Okay, so in order to make this like a triple beam balance, what we'll do is we'll drop it so it becomes level here. When we make it level like this, then the weight of the gas on the left is equal to the weight of whatever's on the right. The weight of what's on the right is tricky because we have this. We have a liquid and a gas. So it depends on how deep you are in the liquid. And so in this particular case, we're this deep in the liquid. And recall, how do we measure liquid pressures? We measure liquid pressures based on the height, not on the actual pressure, just the height of the liquid mercury. And so all we do is we get a ruler and just measure how many millimeters of mercury we have here, and then add that to however many millimeters of mercury we have here. And so let's say atmospheric pressure is 760 millimeters of mercury, and we have 23 millimeters of mercury here. So altogether we'd have 760 plus 23, 783 millimeters of mercury total pressure. And so if we have 783 millimeters of mercury out here, then the gas pressure is the same, 783 millimeters of mercury. And so the pressure of the gas is equal to the pressure of the liquid mercury plus the pressure of the atmosphere. Over here it's a little different. Over here, okay, we made it level like a triple beam here. And so now we have the pressure of the atmosphere. Well, the pressure of the atmosphere is heavier, so the pressure of the atmosphere is going to equal the pressure of the liquid mercury plus the pressure of the gas. Therefore, the pressure of the gas is equal to the atmospheric pressure minus the pressure of the liquid mercury. We'll do some calculations so it makes more sense. And so this is the basic operation of the manometer. We'll look at an example of the manometer later, but basically we just do some addition or subtraction. All right, the pressure inside a steam boiler is 1,427 psi. Express this pressure in atmospheres. And so, do you know the psi to atmosphere conversion? 1 atmosphere is equal to 14.70 psi. So this is the dimensional analysis problem. So why don't you just punch it out in the calculator and see what you get. You set it up so the units cancel. 97.07. Okay, we're allowed 4 sig figs, and so I would go 97.074, and then round that to 97.07. Let's see what they did. So here they have the dimensional analysis set up in this lots one. This is fine, but I want you to get in the habit of showing me the drop digit. The drop digit here was 4. They didn't show me the drop digit. I don't like that. I want to see the drop digit. So you do one extra step here showing it being rounded to 9707. This is a one-step conversion. You don't have to write down all the details for this. The pressure in an automobile tire is 29 psi on a day. Okay, let me talk about the pressure. Let's say you have a helium tank you're filling balloons with. When the helium tank goes empty, is it really empty? Is there a little bit of helium stuck in there? Yeah, there is. You could suck it out. You could try sucking it out. It'd be very difficult though. And so, in other words, when the helium tank goes empty, it's not really empty. It's filled with a little bit of helium or air, In fact, when you buy a helium tank and the tank's to be reused, you never return it empty. If you return it empty, then they have to suck out all the air that got in there because it gets contaminated. And they charge you for it because it's expensive. And so that's what we call gauge pressure. And so let's say if I have a helium tank here. Helium, He, it's a gas. And so let's have a pressure gauge here. If the pressure gauge is reading 0 psi G, G stands for, what do you think G stands for? Gauge. PSI stands for pounds per square inch gauge. A reading of 0 psi G means the tank is empty, but you know what? This tank is filled with air. Let's say air pressure this day was 14.7 psia. Psia is absolute pressure because you didn't suck the gas out of there, create a vacuum. If you suck the gas out of there, do you remember the vacuum? You remember what happens when you suck the gas out of a container? You have to have stuff that looks like this. When you start sucking the air out of the container, you better build that container out of heavy-walled stainless steel. Look how thick the walls are on that thing. Why? Otherwise it's going to implode like a submarine. Crushed. 14.7 pounds, it doesn't sound like a lot, but it's a lot. And so you got containers like this. When you generate a big vacuum, you have to have very thick walls here, otherwise it's going to crush the container. So this is ultra-high vacuum stuff. This is what happens. So if we tried to start sucking the container out of this helium, well, the helium tanks are usually already pretty thick, so we already probably could withstand these pressure differentials. But anyway, so the tank's not really empty. It's empty because the gauge is showing 0. If we wanted to suck out the helium out of there, and we could generate a perfect vacuum, then we go to minus 14.7 psi G. Minus 14.7 psi G would be 0 psi A. That means there's no gas in there. If there's no gas in there, are there any collisions? No, that means absolutely every single helium atom that was in there got sucked out of there. Very difficult to do, but that's what it would be. And so if we're looking at, let's say we're looking at, it's 14.7 psi on the gauge here, or 100 psi on the gauge. This would be psi G, this would be psi G. Okay, if it says 14.7 psi-G, what is psi-A? psi-A would be 29.4 psi-A. If it says 100 psi-G, what is psi-A?
114.7.
Yeah, 114.7 psi-A. Okay, that last 14.7 pounds is very difficult to get out of that helium. You need extremely powerful vacuum pumps. They're not going to do. And so if an automobile tire goes flat, it goes to 0 psi, is that psi-A or psi-G, you think?
0 psi.
0 psi. Automobile tire goes flat at 0 psi. Is that psi-A or psi-G? Yeah, psi-G. You know, if it was psi-A, your tire would just collapse into, you know, there'd be no air in there at all. And so here, this is psi-G, 29 psi-G on a day. The weather report states that the barometric pressure is 30.09 inches. How would you report the absolute tire pressure in kilopascals? Well, first let's report the let's report it in psi, the absolute pressure in psi. Because all the units are all mixed up here. It's okay. And so we should try to be consistent. And so I would do this. You know, this gauge is not relative to 14.7. This gauge is relative to whatever atmospheric pressure is that day. Your tank is going to go empty when the helium pressure is equal to the atmospheric. And that goes empty because it's not going to come out, right? And so you have that. Now, if it's a high pressure day, you're going to have less helium come out. It's going to force it back in. If it's a low pressure day, more helium is going to be able to escape out of the tank. And so it depends on what the relative pressure is that day. So the relative pressure that day is given here. It's 30.09 inches of mercury. Well, 30.09 inches of mercury is how many psi? So let's go ahead and do that in psi. So if we have 30.09 inches, how many psi is that? And so we need the inch. Let's go back and look at the conversions. Now the inch conversion you don't necessarily have to have, but the inch conversion, it should be easy. Because if we know this, we should be able to derive the inch conversion. 1 atmosphere is 760 millimeters. 760 millimeters is 76 centimeters. 76 centimeters is how many inches? So that's 76 centimeters divided by how many inches or how many centimeters per inch? Divided by 2.54 gives me 29.921. And so if I go from 30.09 inches and I convert this is inches of mercury. Then I convert this to 29.92 inches per 1 atmosphere. You might as well do this in psi because I want to do a psi for the gauge. We know that there's 14.70 psi per atmosphere. So let's figure that out. So it's a little bit higher pressure than normal. Maybe it's a nice sunny day or something versus a stormy day. All right, so let's let's redo this here. This is an automobile tire. So the automobile tire, we have some kind of gauge here. Let's take a reading on the gauge here. If this is reading, the gauge is reading, what was it, 29? PSI. The gauge is reading 29 PSI. And then we have 0 PSI here. Now, it depends on the gauge. If you work with automobiles, they have a vacuum gauge. Have you ever seen a vacuum gauge? A vacuum gauge goes in negative. And so on the vacuum gauge, the most we can go negative is negative 14.7 PSI. We can't go more negative than 14.7 PSI. Why? Because at negative 14.7 PSI, there are no molecules. If there are no molecules, there's no collisions. If no collisions, there's no pressure. Right? This is why we call it absolute zero. This is absolute zero pressure. Well, anyway, this is the gauge pressure. So right now we're at 29 PSI. That's what the gauge is reading. But that's not the absolute pressure, because this is on a relative scale. And so this is the PSIG scale. This would be like centigrade or Celsius, you know. Zero really doesn't mean anything. And so if we look at the Kelvin scale is absolute. So this would be 0 PSI A. 0 PSI A means there's absolutely no molecules. 0 PSI G means there's probably plenty of molecules. It depends on atmospheric pressure. Okay, so that means here that at 0 PSIG, then, you know, the atmospheric pressure is equal to the tank pressure, and that is 14.783. And so at 0 PSIG, we're at 14.783 PSI A. And that means at 29 PSIG, what is our PSI A? Oh yeah, 43.783 PSIA. Do you see how I did that? It's just, the scale is just offset. It's offset by 14.78. Now we got to convert that to kilopascals. So this is our absolute pressure here. So if we have 43.783 PSI, A, then we'll just convert to PSI. And that's 14.70 PSI per atmosphere. And then how many pascals? There's 101,325. 101,325 pascals per atmosphere. This one you don't have to memorize much, but if you have physics, then it's easy to memorize because it's a common number. And then we go to kilopascals. There's going to be 1,000 pascals per kilopascal. And so this will give us the absolute pressure in kilopascals. We'll see how the book did it. All right, so the book went straight. They did it combined. I don't like combined conversion factors like that. I like this because when you do the combined, it's just more memorization usually, or more steps. It leads to more confusion. If you have a certain core number of conversion factors that you use repeatedly, then you kind of remember them. If you kind of remember them, then you're less likely to make mistakes. When you start throwing in, you know, combined or composite ones like this, it's easier to make mistakes. I separate it. I'd rather do a couple of steps and combine. define it if you want. So they went straight to kilopascals. We didn't. We went to PSI. But as I said, there are multiple ways of solving these particular dimensional analysis type problems here. But let's see if we get the same answer. Okay, so I'm going to just go ahead and calculate the answer here. 43.783. 43.783 divided by 14.7 times 101.325 divided by 1,000. I get 301.7. 301.789 or 78 kilopascals. Your book likes to round without showing what they're rounding. We got 2 sig figs. How do they get 2 sig figs? Oh, the 29 psig. But you know, that's very tricky because you remember the rules for addition and subtraction. The rules for addition and subtraction say that we go by the number of decimal places. Actually, that would be right. This would be 2 decimal places. This is basically none. I mean, this ends there. So we're allowed this. So the 7's going to be uncertain because the 0s here is uncertain, the 8's uncertain. So this would be 2 sig figs. I carried too many sig figs here. You see that? So in other words, I have 29. What's the uncertain digit in 29? The 9. The 9's uncertain. The 9's uncertain. And then I'm adding 14.783 to that. What's the uncertain digit in 14.783? 14.783, I'm carrying an extra digit, but so I have 2 uncertain digits here, but obviously I'm going to drop one. I'm just carrying one extra to avoid round off. So I have the 8 is uncertain and the 3 is uncertain. So this is one of the 3 subscript digits. I don't want to have 2 uncertain digits in there. And then when I add this, you know, I'm going to have, well, it's going to be 43.783. Where's the uncertain digit now? The uncertain digit is, we're only allowed 1. And so, well, this is going to be uncertain. So this should round to 44, but I don't want to round it to 44 right now. Because how many round-offs am I allowed? Just 1. So I carry it over. And so I get 381.78, and then we got to round this to the 2 sig figs. If we round it to 2 sig figs, we'll call it 3.0 times 10 squared kilopascal. So we get the same answer. This is the absolute pressure, not the gauge pressure. And so we could call it kilopascals absolute. Now, measuring pressure, you know, is okay. We can also measure volume and temperature. Temperature, we just use a thermometer. Yes. Volume, you could do different ways. You know, since the volume is variable, they have this mercury plug that can go up or down. And so this plug can change the volume of the gas depending on the temperature here. And so this is one of the observations. Normally when we start off in science, scientific method begins with observation. And so we're coming full circle back because, you know, we've been doing this. We've been looking at observations, we've been looking at theory, you know, we've been looking at different parts of this. But now we're going back to a more historical perspective. You know, these are the original experiments with gases. The original experiments with gases were set up like this. You know, people were very curious about gases and how they behave. And so one of the things that people were very curious about was what happened with the volume of the gas and temperature. And people noticed that as the temperature increased, the volume of the gas increases as well. Now, does this happen? If I double the temperature, does the volume double? If I triple the temperature, will the volume triple? Is it linear like that, or is it non-linear? And so people were very curious about it, and you know what they found out? They found out if you double the temperature, the volume doubles. But it depends on what temperature you double. So if you double the Celsius temperature, the volume does not double. If you double the Fahrenheit temperature, the volume does not double. It's only when you double the Kelvin temperature, the volume will double. And therefore, for gases, avoid using Celsius and avoid using Fahrenheit, because what happens? You know, if somebody asks you, hey, you know, I want a gallon of gas, it's no problem. But what if you said, hey, I want a negative 1 gallon of gas? If you want a negative 1 gallon of gas, you're asking the person to remove 1 gallon of gas out of your gas tank, right? Or something like that. But, you know, if you're dealing with negative, you know, what does that mean? Does the volume go negative? No. And so this is why, you know, the negative is it's arbitrary, it's not real. This is not a real negative. In that sense. And so, anyway, we got to do it in Kelvin. So this is why, in Kelvin, this is the red temperatures here. So for gases, from now on, we just work with Kelvin. Sometimes we're given Celsius, but if we're given Celsius, we better convert it to Kelvin. Otherwise, you know, we get this screwy thing with the arbitrary zero here. But anyway, this is the relationship here that people saw. They saw what's called a linear or straight line relationship. So this is observation. And so this is volume and temperature. What happens to the volume when the temperature gets to 0? What happens when the temperature gets to 0? What's the volume? The volume is 0. And so at 0 Kelvin, the volume is 0. Now, if we go negative Kelvin, can we get to negative volume? So let's say if I need a negative gallon of gas, I'll just tell them, well, just cool it down to negative Kelvin. You cool it down to negative Kelvin, all of a sudden the world is going to invert, and we're going to go negative volumes rather than positive volumes. Is that the case? No. And so this is absolute zero in two senses. One, absolute zero, because in theory, the gases are going to go down to 0, and you can't go negative. You can only have positive volumes. And two, there's no motion. And so this is observation. This is an observation made by Charles, a scientist. But it's a very simple equation. The volume, which is y, is equal to the slope times the temperature plus the intercept. The intercept is 0 if we're using Kelvin. And so we take our data. What do? We take our raw observations and then we look for patterns. Here's the pattern. And then what do? So we take our raw observations, this data table, we figure out the pattern, which is this graph, and then we get a law. And that law is often called an empirical equation, because empirical means what? And derived from observation versus derived from what? We can derive equations or laws from observation, or we can derive them from pattern is observation. We can derive it from observation, or we can derive it from where did the law of multiple proportions come from? Observation or somewhere else? Oftentimes they have names for these things, like in the theory of, when you start dealing with theory and this kind of things, we have different equations. We have empirical equations, we have semi-empirical equations. You know what a semi-empirical equation is? is an equation that partly comes from empirical observations and partly comes from theory. We have different kinds of calculations. Ab initio. Have you ever heard of ab initio? Ab initio is purely from theoretical. Well, anyway, let's get back to what we were talking about earlier. Here, that's from week 1. You know, week 1 I know is a long time ago. It's easy to forget that stuff. So you want to try not to forget it. And so here's absolute zero, the lowest temperature possible. Minus 273. It's minus 273.15. Sorry, sometimes I forget to write the 0.15 there. Which is minus 459.67 Fahrenheit. So my calculation was a little off because I didn't include the 0.15. Here, motion is stopped. Well, not all motion. You know, inside, within the atom, there are things called electrons. Electrons never stop moving. They can't. And it also corresponds to zero gas volume. You know what this is called? So somebody came up with an equation for this line, and the guy's name's Charles. And so the equation for this line is called Charles' law. Look at Charles' law. I don't know why they didn't put Charles' law on this slide. Here it is. It's a particular level view of Charles' law. And this is Charles' law. What happens with higher temperature? There's more motion. Well, if there's more motion, there's bigger forces of collision. And so at higher temperatures, you just have stronger, more forceful collisions and more frequent collisions. So the higher the temperature, the more motion, the more it's going to increase the pressure and force that out. Now the pressure is equal here. You know, the pressure, as long as this plug is not moving, then the pressure of the gas is equal to the pressure of the air. Well, anyway, what does Charles' law look like mathematically? And so this is just showing the air pressure on top and the pressure underneath. This is what Charles' law looks like. Charles' law said that the volume is proportional to temperature. In fact, the volume is equal to constant times temperature. In other words, this is y equals mx plus b. Y equals mx plus b. Y, volume, m is the slope, t, x, and b, the intercept. The intercept's 0 because at 0 volume we have 0 Kelvin. And so, in other words, this is it. So the volume over temperature is equal to the constant, which is the slope. We don't need that. We could just say volume over the temperature is constant. We'll use this later. In other words, if I double the temperature, what's going to happen to the volume? It doubles. It's directly proportional. If I triple the temperature, the volume is going to triple. That's Charles' law. We often do this with Charles' law. Rather than doing this, you know, we say this. You know, I could start off with volume 1 at temperature 1 and then double the volume. If I double the volume, then this T2 would be 2 times T1, so it would be double V1. Multiply both sides by 2. If I triple the volume, it would be 3 times the triple. I don't know if we're going to use this equation that much, but this is Charles' law. V1, T1. So if I change the temperature, I'm going to change the volume. If I change the volume, I'll change the temperature. That's what it said. So actually, we'll try one problem with Charles' law. A container with flexible walls holds a gas that is cooled from 65 to 22. So if the temperature goes down, the volume should go down as well, with no change in pressure. If the container volume is 4.5 liters initially, what is its volume after being cooled? So let's use Charles' law. This is Charles' law proper. We don't have to worry about the derivation. And we aren't even going to bother calculating the slope. It's V1 over T1. So at temperature 1, we have volume 1. At temperature 2, we have volume 2. And so we're solving for volume 2. So why don't you go ahead and solve this for volume 2. Uh-huh.
Is Charles' law true for like Kelvin or Celsius or Fahrenheit?
No, it's only for Kelvin.
Okay.
It fails for Celsius and Fahrenheit. So that's important. Charles' law does not work for Fahrenheit and Celsius, but they gave us Celsius. And if you plug in Celsius in there, it's going to fail. You would have to know that Charles' law. This is why, you know, this is why not everybody can do this, because you would have to know some knowledge about this equation. This equation doesn't work for everything. Let me know when somebody's gotten the answer.
I got 1.5 2
1.5. That's good. I'm glad you did that. You got 1.8? Let's see what they got. They got 3.9.
I got that.
Can you check that again? They got 3.9. You know, this is Charles' law here, so we're just going to plug in. We're solving for V2. We're going to plug in V1, T1, and T2. Did you use Kelvin or did you use Celsius? Oh, Celsius doesn't work because you have to convert it to Kelvin. The reason is because of the negative. What does a negative, mean? You're going to get a negative volume if you use Celsius. Same thing with Fahrenheit. If you use Fahrenheit, you're going to get a negative volume. You got 3.9? Let's wait just a minute. Do that. I have that. No, this is not for this one. This is just for your personal. If you already wrote it down, I have extra cards, or you can use as many cards as you want. We're going to have a little quiz on a different problem, dimensional analysis. So after you're done with this, did everybody get 3.9? Basically, you have to convert the temperature from Celsius to Kelvin. So they converted it here by adding 273. Because the 0.15 would be rounded off anyway, they dropped it, but we could include the 0.15, we get a little more accurate answer. We got 3.9. But I like what you did, you showed me the drop digit. I want to see that. Temperature decreases, which leads to a decrease of volume. So we're okay. We're going to continue chapter 4 next time, but we're going to drop back down to chapter 3 for this little mini quiz. For chapter 3, I want you to do a little calculation for me here. Where did I put it? Fantastic. We were going to do this problem earlier, but let's do this now. We'll do it as a quiz. Let's see how your dimensional analysis skills have developed. So we're going to do number 71 here. 71. The volume of seawater on Earth is about 330 million cubic miles. If seawater is 3.5% sodium chloride by mass and has a density of 1.03 grams per milliliter, what is the approximate mass of sodium chloride in tons dissolved in the seawater on Earth? How many tons of sodium chloride are present in the seawater, assuming those things here? 71 in the morning? Oh, sorry. Well, it's okay. Do that one. I was planning on 73, but 71's fine. Do 71 and then 73. How about that? See if we have enough time. Maybe we don't have enough time. How late do we go on Tuesdays? 12:20 on Tuesdays? Forget it. All right, that's it. We'll do this tomorrow. Shoot. I was gonna just. Can you turn in the card? Just write your name on the card and just turn it in. Or I'll give you a new card tomorrow. I want to see.
Well, could you send me the back of which one do you want?
This one is fine.